Hi, we are going to see today about the properties of Laplace transform. Okay, last lecture we have seen about how we can compute the inverse transform of Laplace transform, and tonight we are going to see some 6-7 properties of Laplace transform which helps us to compute the transform of a more complex functions rather than using that integration to come up with an S-domain equivalent of that time domain function. We are going to see some properties which would help us to get into that transform much more easily. So the first transform that we are going to see is the linearity. The linearity function, which tells us that the Laplace transform of a times f1 at t plus b times f2 at t is equal to a times f1 at s plus b times f2 at s. So this is just a linearity property, which means if we are asked to find the Laplace transform of the sum of two functions, it is basically the sum of the Laplace transforms. This is what we call linearity, and I think we have already applied this in our previous lecture. For example, if we are asked to find when we try to find the Laplace transform of sine omega t, we used that property where sine omega t is defined as e raised to j omega t over 2j plus e raised to minus j omega t over 2j. Okay, this one is minus here. So if this sum is defined like this, then this is basically the Laplace transform of e raised to j omega t over 2j minus the Laplace transform of e raised to minus j omega t over 2j. So here the sum of the Laplace of the sum is the same as the sum of the Laplace transforms, or the difference, it doesn't matter. So that's the first linearity property. So whenever you have a function which is the sum of two functions, then you can basically take the Laplace transform of each and compute the total Laplace transform. Right, the second property is scaling. By the way, I have already, you can find these properties on your slides. There is a table which has got the Laplace transform of important functions, and there is another table which has got the scaling. Alright, so scaling tells us that if the Laplace transform of a function f of t is f of s, then the Laplace transform of f at at is going to be 1 over a times f of s over a. Which means if you multiply your time function by a scaling here, in the frequency domain it's going to have to be scaled in division. So for example, we already know that the Laplace transform of sine omega t is omega over s squared plus omega squared. So what if we are asked to find the Laplace transform of sine 2 omega t? You see this 2, how it is a scaled version in the time domain. Then rather than using integration from 0 to infinity and computing it minus st sine 2 omega t dt, rather than invoking that transform, we can simply use that and just take, instead of a, we have 1 over 2 f of s over 2, which would be 1 over 2 multiplied by, in the place of s, I'm going to add s over 2 squared plus omega squared. So that would give us 1 over 2 omega over s squared over 4 plus omega squared. So that can be simplified further, but to make our point here, that would be enough. So this is our second property. Alright, third property that we are going to see today is time shift. We have already seen what time shift means in step function. You remember when we saw a step function u at t, it's represented by a function which starts at 0 and has magnitude, and when we time shift this function, it would give us, it would shift, for example, here with a, then this function is t minus a, and if it starts from here, it will be t plus a. So time function, time shift. If this is time shift, then the Laplace transform of, if the Laplace transform of a function f at t is given by f at s, then the Laplace transform of the time shift f minus t, f of t minus a, is going to be multiplying that time function or that frequency function, frequency domain, by e raised to minus as. So in other terms, as we have seen last time, for example, if we are asked to find the Laplace transform of cos omega of t minus a, then that's simply, rather than using that tedious integration e raised to minus a minus st cos of omega t minus a, rather than using that, we can simply just plug this e raised to minus as multiplied by f of s. In this case is going to be s over s squared plus omega squared. So that would give you s times e raised to minus as over s squared plus omega squared. So that's our third property. So the Laplace of f of t minus a is, it's just like multiplying the f of s, or the Laplace transform of f of t, by e raised to minus as. So that will be our time differentiation or time shift. A shift in time is expressed as a product of e raised to minus f as. And the fourth is the frequency shift. So we have seen here a time shift. Now we are going to see a shift in frequency. And this rule is expressed by what brings a shift in frequency, what gives us f of s plus a. What brings a shift in frequency? A shift in frequency is found by taking the Laplace transform of e raised to minus at times f of t. So if you know the function f of t, and if it is multiplied by a decaying function, then that's the same as a shift in the frequency domain. For example, we already know cos omega t is s over s squared plus omega squared. So if we are asked to find the Laplace transform of, so this is the Laplace transform of cos, if you are asked to find the Laplace transform of e raised to minus at cos omega t, which is a very common function, then rather than coming here and integrating from 0 to e raised to minus st e raised to minus at cos omega t dt, rather than integrating that, we just plug it in here. So we would compute f of s plus a, which is s plus a. In the place of s, we will substitute s plus a. So it will be s plus a squared plus omega squared. That's because we have this frequency shift property. So anytime a multiplication of a decaying function in the time domain is the same as shifting the frequency. Why is this function important? If we plot e raised to minus at, what do we get? e raised to minus at is a decaying function like that, and cos omega t is a trig function. So if we multiply these two, we are going to get a very common decaying trig function like that, where the envelope is the decaying exponential function. Alright. Okay, the next one is we have already seen a frequency shift. Now we are going to see time differentiation. Like I said earlier, we would refer back to these properties of Laplace transform in order to get the Laplace transform of a more complicated functions. So whenever we encounter this, we have to refer to the frequency shift property rather than just taking the long way to integrate and get the result. Alright, the time differentiation function tells us that if the Laplace transform of f at t is done, the Laplace transform of f at t is f at s, then the Laplace transform of the derivative of f at t the Laplace transform of the derivative of f at t is always going to be a multiplication of the Laplace transform by s subtracted by f of 0. And the second derivative, which is sometimes referred by double strikes here, is represented by the second derivative f at s minus s times f at 0 minus f derivative at 0. Well, we will just concentrate on this one. So this helps us, for example, to find the Laplace transform of sine omega t. We have already found this using different properties, but if we know the Laplace transform of cos omega t, which is equal to s over s squared plus omega squared, what is the Laplace transform of sine omega t? We know that if f of t is cos omega t, then f derivative of t is equal to what? F derivative of t is always minus omega sine omega t, which means the Laplace transform of sine omega t is going to be minus 1 over omega times the Laplace transform of f of t, right, which is, or the derivative, the Laplace transform of sine omega t, which is going to be minus 1 over omega multiplied by, if we use this property here, then it is going to be what? S times f of s minus f at 0. So in this case, we know that f at 0 is 1, f at 0 is 1, and f at s is already given here, which means it's going to give us minus 1 over omega s times f of s is s over s squared plus omega squared minus 1. So that gives us omega over s squared plus omega squared, which is the Laplace transform of sine omega t. So this is a very important property, which is called the time differentiation property. So if the Laplace transform of a function is f of s, then the Laplace transform of its derivative is found by multiplying the frequency domain by just s. Okay, what about, this is time differentiation. What about time integration? Time integration is seen as what happens. We know that the Laplace transform of f at t is equal to f at s. Okay. So what would be the Laplace transform of integrating from 0 to t of f at t? So this formally this is the integration from to t of the integration from 0 to infinity of e raised to minus st f at t dt, right? Rather than taking that double integral, what do we get? This is the same as 1 over s f at s. So it is just dividing the Laplace transform of f of t by s. As an example, let's see. For example, we know that the Laplace transform of u at t is 1 over s, right? And we know that if we integrate u at t, it gives us t, right? Which means the Laplace transform of the integration of u at t as per this rule should give us 1 over s times the Laplace transform of u at t, which is 1 over s, which is 1 over s squared, and that's correct. The Laplace transform of the t function, which is ramp, gives us 1 over s squared. Okay, I think we have one more, which is frequency differentiation. Alright, the frequency differentiation tells us that if the Laplace transform of f of t is f of s, then if we multiply f of t by t, this is the same as differentiating the s domain and multiplying it by a negative number. So for example, we know that the Laplace transform of e raised to minus at is 1 over s plus a, right? Which implies the Laplace transform of t times e raised to minus at, even though we can take the long root, which is e raised to minus st times e raised to minus at times t dt, but just applying the rule here, we take the minus d per ds of 1 over s plus a, which is going to be 1 over s plus a whole squared. So that will be our frequency differentiation rule. So all these properties help us to come up with some easier ways to differentiate, to get the Laplace transforms. So just to revise what we have been looking at, the linearity property here tells us that the Laplace transform of the sum is always the sum of the individual Laplace transforms. Scaling tells us that if the time domain is scaled, in the frequency domain it will be divided by that scaling factor, and we take the Laplace transform of s over a. And time shift tells us that if you shift it in the time domain, in the Laplace domain, it is the same as multiplying it by a decaying frequency function. And if you multiply it in the time domain by decaying frequency function, in the frequency it is just shifting it. That's why it's called frequency shift. Time differentiation: if the Laplace transform of a function is f of s, then the Laplace transform of a differentiation is s multiplied by f of s minus f at 0. And time integration: if a function has a Laplace transform f at s, the integration of that function gives you 1 over s. These two are important. We are going to see current voltage relationship in capacitors by integration, which means that would be the capacitance equivalent in the S domain, and we are going to see S times F at S for inductor. And here, time differentiation, if a function is multiplied by t in the time domain, it is the same as differentiating its frequency domain, d per ds. Thank you very much. Next time we are going to see the initial and final value theorem. Thanks.